Okay, welcome back. I can't resist doing a lecture regarding the transformation of the electromagnetic field tensor using an example that I'm going to draw from a really wonderful paper. Let me present the paper to you so you can go to it. If you're part of the uh, Patreon group, you should be able, I'll put the paper in the folder for accessible papers. Not too much else is in there, but I'll make sure I do it. And here it is, Moving Dipoles and the Relativity of Simultaneity. Now, there's a lot in this paper by Mr. Redfern that is fascinating. It covers a lot of the stuff we talked about, especially when we did our paradoxes. The notion of simultaneity is a real trick, and it will catch you by surprise if you're really into the subject. Uh, but I'm extracting from this paper just his notion of the idea of moving dipoles, and we're going to talk about the transformation of the electromagnetic field tensor, and we're going to study moving dipoles. And we don't literally do it the way he does in this paper, although it's extremely close, and believe me, there's no way I would have drawn through this without the guidance from the paper. But we're going to do this because we've just developed the electromagnetic field strength tensor in the previous lecture, right? We went all the trouble to develop this guy. Now we're just going to make sure we understand how it transforms and to sort of chew on it a little bit before we move on. So the basic idea is that we're going to study a magnetic dipole that is in relativistic motion. And we're going to do it initially with our sort of gut intuition, and then we're going to actually do the real transformation and compare. So let's begin. Now, the gut story is pretty simple. We start with a current loop. Now, we're going to treat this as a dipole. A true current loop actually is a multipole object. But if you make it infinitesimal and take the right limits where you boost the current and shrink the size, you end up with what we call a pure dipole field, right? A pure dipole. So understanding that there's really no true manifestation of a pure dipole, magnetic dipole, we will still take those formulas of a pure dipole, and those are what we're going to transform. Now, roughly speaking, you would think, okay, if I put this pure dipole in motion with a velocity v, and I sit on the ground so that I'm in the lab frame, watching it, and there's two effects that I would notice. The first is length contraction along the direction of motion. So I would kind of get this oval-shaped object, which I'm kind of drawing as a bit of a rectangle just for illustrative purposes. But it would definitely shrink only in the direction of motion. And there is this current going around it, right? So what would happen is as the two sides got together, I would expect that the flow of current in one direction would be canceled by the flow of current in the other direction. And this would really affect this notion of a pure dipole because these two currents would tend to cancel out, right? As time goes on, this gets closer and closer together, and these currents are literally on top of each other, canceling out. So there's actually no current flowing in the up and down direction, right? That's sort of the intuition about how this should work. Likewise, as this velocity gets faster, the current is flowing in a circle, and it's got a drift. The electrons have a drift velocity, although this is current, so the electrons are actually flowing the other way. So, but we're just going to say the charge is flowing in this direction, following the arrows. Well, up here, the velocity of the charge is is v plus the drift velocity. The little v is the drift velocity, and capital V is the frame velocity. But down here, it's v minus v. Now, when I write v plus v and v minus v, these are the relativistic additions, right? So this is implied to be the relativistic addition of velocity. I might want to put this with a little r here just to make it really clear that these are the relativistic additions. But the point is that the charge is spending more time down here and less time up here. So there's a charge buildup, so the myth goes, and what we end up seeing is an electric dipole forming. So we see less and less magnetic dipole and more electric dipole as the velocity moves on, right? That's sort of the idea. So what we're going to do is we're actually going to transform the pure dipole, magnetic dipole field using the relativistic transformations we've already learned, using the methods we've already learned, which are different than different than Mr. Redfern's, but they kind of get us to the same place. So let's begin with that. So we begin with our idea of the electromagnetic field tensor, which we've written in contravariant and covariant forms. And for those of you who have followed through my What is a Tensor lesson, there are basis vectors associated with the coordinate basis. And this tensor is a tensor field. So it's a function on space-time, right? So there's some coordinate system out there, and that coordinate system is x alpha, and each point x alpha, you get a field tensor. And the field tensor has all these components, right? And we know that it's antisymmetric. So we know that there are, let's see, what is it? 6 independent components. Yeah, 6 independent components. Now, here's where things get a little weird, and you have to, that's why I'm kind of doing this lecture, is I want to make sure you avoid pitfalls. If you go to Jackson, say, the famous field theory, classical electromagnetism book by Jackson, and almost everybody else actually, you'll see this kind of thing. You'll see the contravariant form of F expressed as a matrix, and that matrix could be just called F. And I put this equal sign in quotes because you really cannot think of an object with 2 up indexes or 2 down indexes as a matrix and then just dive straight into linear algebra. You have to be very, very careful with this. But they do this, so we are going to follow this because it's so commonly done. But I want to make sure we take it very carefully. So we're going to call this matrix the matrix F. And it is related to the components of the contravariant components of the electromagnetic field tensor. So this is the 0, 0 component, the 0, 1 component, the 0, 2 component, the 0, 3 component, right? The 1, 0 component, the 1, 2 component, and the 1, 3 component, right? So that's how we understand this. We understand this as a matrix that's populated by the associated component of F. But I really want to, the reason I want to make sure I emphasize these scare quotes is that I really don't want students associated with my teaching to think of this as a matrix. However, I have to relent because it's done so much, right? If it's done in Jackson, what can I do about that, right? Now, the other matrix that's important to us is the Lorentz transformation matrix. And right now we are going to write that matrix exactly like this form. And actually, interestingly, you can write this as an actual matrix. This really, really is a matrix. When you have 1 up index and 1 down index like this, you can in fact call that a matrix. So there's no scare quotes here, right? Now, because we've chosen these entries, this is our standard Lorentz transformation, it should be clear that this represents a Lorentz transformation in the minus, with a velocity of minus v between the 2 frames, only in the x hat direction, right? So right now, just by looking at this matrix, we should be able to see that we have a frame that is moving in the minus v direction, right? So this is the lab frame, and this is the moving frame, right? So now normally we would call this frame S prime and this frame S, and we would call the velocity between the two minus v, right? However, I'm going to try to set this up the exact same way the paper sets it up, right? And the paper sets things up a little bit differently. So we'll show you that later. But understand that if we have a transformation matrix, you should be able to look at it and kind of figure out where it's going. Now, this is obviously very simple, right? There's no rotation involved, right? And the boost is all in one direction. It's perfectly symmetric, right? That's the giveaway that this is not a rotation at all. This is a perfectly symmetric uh, Lorentz transformation. So this is a boost in the minus x direction with speed v. Now, the true transformation formulas that we learn using the notation that I most favor would be straight up looks like this, right? It's these Einstein sums executed on the electromagnetic field tensor, converting unprimed indices to primed indices. So this is the unprimed frame, which we're transforming from. This is the primed frame, which we're transforming to, right? Now, it turns out the paper does this in reverse, right? So we got to keep track of that. I'm not adverse to introducing it this way and then flipping it, because you just have to be agile like that. It's as simple as that. Now, if you go to Jackson's Electromagnetism, the sort of definitive graduate text in electromagnetism, he makes it clear in his book that the primed frames electromagnetic field tensor, when it's understood to be a matrix like this, right? Actually, in this case, I should kind of get rid of the scare quotes, right? Because this thing is supposed to be literally a matrix, right? When the scare quotes belong over here, because I don't want you to think of a tensor as a matrix. But this literally is defined as the matrix whose entries are given by these tensor components, right? So this actually is a matrix, and this actually is a matrix. So so what Jackson's basically saying through his work is this transformation can be executed as though the field tensor were a matrix if we understand that we have to take the transpose of the Lorentz transformation matrix on the right and the Lorentz transformation matrix itself on the left. If you do this, right, you end up the same as if you did this, right? So what they're doing is they're kind of manipulating the matrix multiplication mechanics to imitate this formula, right? And you have to trust them, right? Or you could work it out and just see that this, in fact, is in these sums that are all implied, this double sum really that's implied in this is duplicated by this process. So whenever you're going to prepare yourself to do Lorentz transformations of tensors, if you're working with a reference or you're working with a book, you really got to step through and see, do they want you to use some sort of weird matrix thing that they've invented themselves? Do they want you to use the literal formula that is actually directly derived from the core tensor analysis of the physics? And it's all fine. It's just make sure that you understand what methodology you're using. We are going to, since we derived so much from Jackson, we're going to go ahead and use this to demonstrate our process. Okay, so now in order to use this, we have to create this matrix F using the tensor components. And to do that, we have to know the electric field and magnetic field of our starting condition, and we have to know our setup in order to understand this guy. So let's do that now. So the setup, as I've deduced it from the book, from the paper, is actually like this. The prime frame is the frame that contains the magnetic dipole, right? So the magnetic dipole is moving. It's moving to the right with speed v. The unprimed frame is the lab frame, which I guess I always put a little person in the lab frame. And the lab frame is moving to the speed minus v relative to the prime frame. So the magnetic dipole is motionless in the prime frame. It's also centered at the origin in the prime frame. I haven't drawn it that way, but this is centered at the origin in the prime frame. a field point in the prime frame is given by r prime. So if I want to know the field at this green point, I take the pure dipole field, which this is not drawn as a pure dipole field, but I've drawn it as a sort of Amperian loop dipole. But understand that we're assuming this will be a pure dipole field. I take a field point r prime, which is going to be far away from the dipole. So we're dealing with the far field. So even if this was not perfectly pure, it gets cleaned up because r prime is large and all the higher multipole terms of this little loop go away. Anyway, I know the formula for a pure dipole based on the vector r, and r will have three components, right? R's components are x, y, and z prime, right? Because this is the prime frame. So in this paper, the prime frame is the rest frame of the dipole. And we're transforming to the lab frame, which means we're going to transform from here to here, and we're going to use a minus v to do the transformation. So I know the field tensor here in this frame, and I'm going to transform to a frame that appears to be moving at minus v uh, relative to this. And so that is why we have chosen this matrix, right? Because this is a minus v in the x direction transformation, which is exactly what this is. All the velocity is purely in the x direction. And this is the prime frame, and this is the unprimed frame. So that's the setup.
Now that we know the setup, we start building our tensor. And we will begin from the classical expression for the magnetic field of a pure dipole. And I'm going to, this isn't the one that I'm totally familiar with, but this is the one that, well, I mean, they're all the same, but this is the form that is used in the paper, so I'm going to copy it here literally. Of note is that you've got this vector expression up here. This is a vector expression, so everything with a little arrow on it is a vector, and it's in the prime frame, right? Because the way we set it up, we've got a dipole that is stationary in the prime frame. So this is the formula for a stationary magnetic dipole. Notice that r, the field point, is given in full vector form in the numerator here, but there's two extra factors of the magnitude of r in the denominator, which really normalize it. There are many versions of this where you'll see r hat, which is the direction of the field point, and then this is cut down to the cube. And that's famous, right? That dipoles, be they magnetic or electric, fall off with the cube of the distance from the field point. So, but in this form, we leave it with the full vector up here. And this has components in all three directions. Now, this looks a little bit intimidating. This is the magnetic moment, right? M is a magnetic moment vector in the prime frame. And the field point, so we want to break this apart. But this is actually really simple because one thing I forgot to mention in the setup is that the magnetic moment is aligned in the z direction, right? So the magnetic moment is simplified by just putting it in the z direction, just like it's drawn here, right? The other thing that's not completely clear here is that this Amperian dipole is actually at the origin of the coordinate system, too. That's another thing that should be made clear because the way the coordinate transformations are done, this guy is treated to be at the 0, 0 center. So r is the pure radial distance, x prime, y prime, z prime. Now you'll notice that t doesn't show up in this at all, right? Which shouldn't be a surprise for anybody who's taken and studied electromagnetism. This is a magnetostatic situation, right? The situation is magnetostatic, meaning we have steady currents that have been in existence forever and will continue to be in existence forever, no dynamics whatsoever. So with that in mind, we should tease this apart. We're going to be teasing this apart a couple times. So let's start now. And I've kind of blown it up over here, right? The magnetic moment vector is just the magnetic moment and in the I direction. I'm going to use I hat. So x hat, I hat, r, x hat, right? All of those things mean the same thing. I'm sure I'll screw it up and I'll use an x hat when I mean an I hat or an rx hat when I mean an I hat. But understand, whatever form I use, I'm talking about the unit vectors I, j, k. So this will be I, j hat, k hat for x, y, and z. But regardless, the magnetic moment of our dipole is aligned in the, whoops, see, I've already screwed it up, right? It's aligned in the z hat direction, so that'll be k hat, right? And then and m dot r, right, the magnetic moment dotted into the field point, is just going to be m z prime, right, where z prime is the field point. Because remember, r prime, the vector, is simply the x component of the field point plus the y component of the field point plus the z component of the field point, right? So when you complete this dot product, the only thing that survives is this z component. So you get m times z prime. Oops, these are all primes, right? Because we're in the prime system. And then, so this is a number. mz prime is a number. So I take that number and I multiply it by the field vector, and I get mz prime x prime I hat, mz prime y prime j hat, and mz prime squared k hat. So this numerator term is simply this thing here, mz prime x prime, mz prime y prime, and mz prime squared. And the reason that's important is because it allows me to take this expression and break it up into its three components. The x component of the magnetic field is 3mz prime x prime over r to the prime to the fifth. The y component, mz prime y prime over r prime to the fifth. And the z component is mz prime squared over r prime to the fifth. And this piece here, of course, is purely in the k hat direction. So you get this extra term of m over r prime cubed. There's no field vectors to normalize in this term of the expression. So you end up with the cube in the denominator. So these are the three components of the electric and of the magnetic field. There is no electric field because I said this is sort of a magnetostatic problem. There's no charges floating around. The current is moving in a steady current loop. No charges accumulating because we don't have that situation we talked about earlier where we're guessing that because of Lorentz contraction, there'll be some time dilation issues and charge will accumulate. None of that's going on. This is totally stationary, going in a circle, no charges, so there's no electric field. So this is a purely magnetic field, magnetostatic problem. And these are the components. So with these components, I now know how to construct my magnetic field tensor in the frame that is stationary with this dipole. And that is, I just plop those components right in where they belong. And I get, for example, this term here, right, is minus bz, and this term here is by, and this term here is minus bx, and then the symmetric, anti-symmetric components make that bx, right, and then make this minus by and make this bz, right? So I just plop them right in there, and I have created my scare quote version of the electromagnetic field tensor. Basically what I've got now is I've got a way of finding each component of the field tensor by just looking it up on a table, right? That's one way to think about it. Or I can say, no, I've created an actual matrix, which I'm going to call the electromagnetic field tensor matrix, and this is it. So because of the way we've set it up, this is the prime matrix in the prime coordinate. So you give me a coordinate in the prime system, this matrix will return the electromagnetic field components in the various directions for this particular magnetic dipole, which is located at the origin. And now it is our job to discover the electromagnetic field tensor in the unprimed system, right? So we're going from the prime to the unprimed system. So let's do that.
Well, I just noticed if I'm going to call this the prime system, then here I should prime these indices using the system the notational system I'm using. An alternative notational system would be F prime alpha beta, but I like to prime the indices for what it's worth. Okay, so we're going to do the transformation now, and this is the transformation formula that we are going to deal with. This is right out of Jackson, except that we've switched prime and unprime because we're going from the system that we've named prime to the system that we've named unprime to be consistent with the paper. But that shouldn't change the overall formula because we've created the correct Lorentz transformation matrix. And so we need its transpose to do a matrix multiplication on the right, and it's the regular matrix to do the matrix multiplication on the left. But since we are using a pure Lorentz boost in just the x direction, everything is nice and simple. The matrices are symmetric, so the transpose and the matrix itself is the same. And this is the matrix expression represented by this formula from Jackson's textbook. And the reason we're comfortable with it, I'll just say one more time, is we're using all of Jackson's notations here, so we trust that he's figured this out correctly. But the index notation is really the fundamental result that we need to remember. You won't see this much in field theory. I just want to prove that you can do these Lorentz transformations and start thinking in terms of the field tensor. So this is just sort of an exercise of all that. But after you do this multiplication, first of all, you realize there's a heck of a lot of zeros in the way we've done it. That's all based on the setup, right? The setup gives us a lot of zeros. Now, we can't get away from the fact that the dipole has components in all three directions, right? But you can imagine if it was some other magnetic field that we were interested in, you would be able to get away from that. You would align some element of the magnetic field so that you would get some extra zeros in here. But a dipole has components in all three directions, which is an important fact we'll be using later on. So when we complete this multiplication, we end up with this matrix. This body part of the matrix right here, the magnetic field part of the field tensor, doesn't change except for the introduction of these blue terms, which are just gamma, right? So gamma pops in, and it doesn't even pop in everywhere. It doesn't pop in on the x components. It just pops in on the y and the z components. So not a lot happens, but you do get these gammas, so that is a thing. So those components basically are scaled by a factor of gamma. So clearly the magnetic field has changed the transformation has made a change of the magnetic field. But what's really critical is the introduction of components in these two time-like parts of the matrix. And those, of course, are electric fields. This is the electric field in the y direction, and this is the electric field in the z direction, right? And these are the opposites of those. So we definitely see that our intuition is paying off a little bit, right? With the idea that charge would accumulate based on just this Lorentz transformation seems to actually hold up, because if we have charge accumulating, it will generate an electric field. And we definitely see electric field happening here. So is this our answer? I mean, the way we've written it, it sure looks like it's the answer, but it really is not quite the answer. And the reason it's not quite the answer is because although we have calculated this matrix for F in the lab frame, if you look at the components, they're still expressed in terms of the frame of the dipole. So because of that, you've got this weird hybrid object right now, which is the magnetic field components in the lab frame, but expressed in terms of the positions of things in the dipole frame. And this, by the way, is only good at the moment that the two frames are aligned, for what it's worth. But we'll get to that in a second. So what we've got to do is we've got to convert this argument from the dipoles frame to the labs frame. And so all of these R primes and Z primes and Y primes and X primes, they have to become R, X, Y, and Z. So let's turn our attention to that, which I have done over here. So R prime is simply expressed as x prime I, y prime j, z prime k. And R is expressed as x I, y j, z k, right? So the field point vector in both frames. I guess if I wanted to be correct, I should put little vectors on these things. Okay, so now the transformation R prime expressed in terms of the coordinates in R, meaning the coordinates in the magnetic dipoles reference frame with respect to the coordinates of the lab frame, since all the velocity is just in the x direction, and we're taking the two frames to be aligned, meaning the moment that their origins coincide and their axes coincide, their spatial axes coincide, uh, all we end up with is a gamma factor affecting the direction of the motion, right? So R prime is going to be, the coordinates in the dipole frame is just going to be the same as the coordinates in the lab frame, with the exception that all the x coordinates are going to have this factor of gamma introduced. And so with this, in principle, we could replace all the R primes with R's. But we're going to do a little bit more care just because the paper kind of goes through this. Well, it doesn't quite go through all the algebra. Special relativity algebra is really annoying, but I definitely worked through it. So what we're going to do is we also need the magnitude of R, right? We need the magnitude of R for these denominators. Right? All these denominators are magnitudes of R. And they're to the fifth power and the third power and all these crazy things. So we're going to find the magnitude squared of R prime in terms of the coordinates of R. And what we just do is we square each component, right, to get the magnitude squared of R prime. But this is now in the lab frame, right? These are coordinates in the lab frame. And I noticed that x squared plus y squared plus z squared, that is the square of the field point vector in the lab frame. So I'm going to create this complex little thing that recovers this, but introduces the value of R squared. And if you look at this, you know, if there was a gamma squared here and a gamma squared here, then the whole thing would be gamma squared R squared. But there isn't. So we add the gamma squared Y squared and the gamma squared Z squared to it, and then we subtract then we add just a plain Y squared and Z squared. So these two terms come from minus Y squared Z squared, and then the extra gamma squared Y squared Z squared is hidden in here, and we subtract those off. So this does in fact equal that, for what it's worth. The reason this is important is this Y squared Z squared part, right? If we now build a little triangle, let's see if I think I've done that somewhere. Yeah. The Y squared Z squared, if we construct this triangle, you know, we have our velocities in the x direction. The field vector in lab frame is some vector r, right, of length r, and we know that the perpendicular distance above this plane is going to be z squared y squared, right? We know that, you know, r has two components. It has z squared plus y squared square root, and it has x. And this value, z squared plus I squared, is going to be r, this magnitude, projected into the line perpendicular to x, right? So you get r sine alpha, and there's some angle alpha that r sub 10. So what you're doing is you're trading z squared y squared for an angle variable, right? So everywhere I see z squared y squared, I can replace it with r squared sine squared alpha, where I understand alpha is the angle between the x-axis and the field point vector in the lab frame, right? So that substitution is doable, is allowed. And this is exactly where I make that substitution. I take the y squared z squared, I make it r squared sine squared alpha. And then I do a little crazy algebra. I pull out a gamma squared r squared from this whole thing, and then I compare terms, and I end up with this expression, 1 minus 1 over gamma squared. Well, that's v squared over c squared, right? Or if I use units where c is 1, it's just v squared. So I replace this with v squared, and now I'm getting gamma squared r squared 1 minus v squared sine squared alpha. And that equaled, remember, that equaled r prime, the magnitude of r prime squared. So now the length of that vector, just without the vector symbol, just the pure length of that vector, is the square root of this thing. So there I have it. I take the square root of the first factor, there's the square root of the second factor. Now I know I need r prime to the fifth, so I can construct that. And I know I need r prime to the third, so I can construct that. And let's see. So now, armed with those things, I can replace these r primes to the fifth, these r primes to the third. I can also replace the z primes and y primes with just z and y, because I know that there's no change in those coordinates because they're transverse to the direction of motion. X, however, has to be replaced, x prime has to be replaced with gamma x, right? Because there is an effect in that direction of motion. So now I can start making these changes in every one of these pieces of the matrix. So what I'm actually going to do is recombine these terms. I'm going to recombine them by pulling them out of the matrix with the appropriate gammas, and I'm recombining the B fields, right? And I've got the I, J, K, and I've got these gammas in here, and now I need to do the substitutions. And after we do all those substitutions, there's the substitution for r to the fifth, and there's the substitution for r to the third. Now you see gamma to the fourth here instead of gamma to the fifth. Remember, our substitution looked at a gamma to the fifth, r to the fifth, right? And the reason you see a gamma to the fourth is because this term has a gamma in the numerator, or the j term has a gamma in the numerator. This k term has a gamma in the numerator. These three terms are what's combining for this, right? This term gets a gamma in the numerator once you write down x prime equals gamma x, right? So here, this term's just y prime goes to y, z prime goes to z, z prime goes to z, z prime goes to z. So the conversion everywhere is simple except this one goes to gamma x. So now you have a gamma in each of these terms, and so it just divides out and you get a gamma to the fourth. And then look what you have. You have a zx, zy, and z squared, which we've already figured out was the dipole moment dotted into the field vector times the field vector, right? So these guys here combine vectorially into this expression right here. The denominator gets this r to the fifth, 1 minus v squared sine squared alpha, and this guy gets gamma squared r cubed, 1 minus v squared sine squared alpha. This becomes gamma squared because the gamma appears in this term right from here, right? From here. So that distributes right in and hits that that second part of the z component. So anyway, this guy becomes in vector form this expression, and this is now this was the magnetic field in the lab frame expressed in the coordinates of the dipole frame, and this is now the magnetic field in the lab frame expressed in the lab frame, and you get this. Now, I could deconstruct all of this and put it back into the matrix to get the final matrix, but that's not very helpful. I think we all understand what's going on here. What we will do is we will take this gamma to the fourth, we'll multiply the numerator by gamma and we'll multiply and divide by gamma. And so we end up with gamma m as the magnetic moment. And then we have r to the fifth downstairs. Same thing up here. We have gamma m and r to the third. And now this looks exactly like the original formula for the magnetic moment. right? We have 3 times the magnetic moment dotted into the field vector times the field vector over the distance to the field point to the 5th power, and this term likewise. But now we have basically the same formula with a gamma here and here. So the magnetic moment seems to be factored by gamma. And then we have some intricate stuff down below. So if I were to look at this intricate stuff down below, right, which is this material right here, right? I'm going to now make that gamma to the 5th, make that gamma, make that gamma, make that gamma cubed. These two, they're basically the same, but notice it's got a velocity squared, and the units are implied here are c equals 1, right? So we have c equals 1. So velocity squared, in the low velocity case, we could ignore that whole term, and then this goes away and that goes away, or it becomes 1 is what it does. I mean, I guess the way to say it is this term goes to 0 and that term goes to 0, and this whole thing goes to 1 and this whole thing goes to 1. And then it looks exactly like a magnetic dipole where the dipole moment is affected by gamma. But then I would say, well, if v is that small, then gamma's 1. So it's really not much of a change of the dipole altogether. But it still looks a lot like a magnetic dipole. But look, it's not a magnetic dipole. This term makes it not a magnetic dipole. Simple as that. And so that kind of jives with what we thought. You know, the deformation of this shape means something's going to happen, and you're basically going to get a different type of magnetic field that's not pure magnetic dipole anymore, but it will be a multipole field of its own right, and it'll have a dipole component, but it won't be, but it isn't pure dipole anymore. So that's kind of important. And the way the paper does it, the paper makes an additional substitution that I've indicated here, but the paper goes out of its way to emphasize this point by taking this term and converting it into this expression here. Basically, it gets rid of this gamma to the 4th, and it does so using, getting from here to here wasn't that obvious to me, but the point is that he found it, the paper found it a little easier to interpret the relativistic limit of this denominator as opposed to this one. But the algebra to go from here to here, I actually did it in blue down here, so for what it's worth. He also in the paper, he retains that factor of C, right? So much for, that's the transformation of the magnetic field, but we also know that we picked up these electric field pieces. So what can we learn about the electric field? Well, the electric field, I'm not going to go nearly into as much depth as he did in the paper, but if I have all the components I need, that's a full description of the electric field, and I just need now to convert the coordinates. So I'm assembling the full description here. This is now the electric field vector in the unprimed system given the prime coordinates, and now this is the electric field vector in the unprimed system in the unprimed coordinates after I make all of those changes. And for some reason now I'm using z hat and y hat, but here's the kicker, right? If you look at this, what you discover very quickly is there's no x hat. There's no x hat, no x hat. So this electric field that is produced because of the motion, right? Because of the Lorentz transformation, the electric field that we see in the lab frame, whatever it is, it has no x component. So now this is the formula for the electric dipole field, which is very reminiscent, of course, of the magnetic dipole field. And if you look at this numerator, and we assume a polarization in the z direction, just like we did before, you see there is an x hat component, or I guess, I can't believe I did this, an I hat component, right? J hat. I knew I would screw this up. So this is K hat, J hat, and this is uh, I think I messed this up too, right? This Y hat should be a Z hat, and this Y hat here should be a Z hat, which should actually be a K hat, right? But anyway, the point is that there's no X hat. And the point is that this numerator in the real electric dipole does in fact have an X hat if it's aligned in the Z direction. And so we can immediately see, just by that fact alone, that tells us immediately that this guy, or that these two components here, and you see there's no X component, right? I mean, that was obvious from the matrix actually, right? I didn't even need to break it down and add it up and say, hey, wait, where's my X component of the electric field? It was obviously never there, right? Because these two numbers are zero. So the point is that this guy here, which is the electric field in the lab frame of this moving dipole, is not an electric dipole. It is something else. It is this thing. This is what it exactly is, because our transformation is not wrong, but it is not an electric dipole. And that allows us to go back to the beginning and say, well, you know, we were kind of onto something. We definitely were right that charge is kind of accumulating, but this is not, because it doesn't matter how fast the velocity is, you're not going to turn this expression, you're not going to develop an electric field in the direction of motion, no matter how fast you're going based on this. So you're never going to get a pure electric dipole in the limit. You're getting something else. And so we've accomplished the goal of this. We've done a transformation of the field. We've done a full example of the transformation of the field. I chose a non-trivial example just because it's fun and also does a little bit of vector math, but it also should whet your appetite as to, okay, well, what gives? What's wrong with this picture? And Mr. Redfern explains it in great detail, and it has a lot to do with how we really didn't take into account notions of simultaneity in this problem, which is very similar to the issue we had when we did our paradox of the rod and the ring. So there's some version of the rod and the ring that manifests itself here. So when I talk about current in this direction, current in this direction, and all this, I'm talking about a snapshot in time that doesn't really exist. I need to talk about things that are simultaneous in the lab frame, and I need to look at the simultaneity of this in comparison to the moving frame. And he discusses this in great detail in his paper. Okay, so we've pretty much we've accomplished all the goals that I was interested in getting at, not only in this lesson, but we've now converted our thinking to the four potential formulation of electrodynamics, which we've now turned into a four potential. And we now have the electromagnetic field strength tensor, and we've understood in detail how Lorentz transformations work. So now all of these symbols that show up in QED books in the early chapters should make a lot of sense. And you should feel real comfortable with this stuff now, you know, because we've worked on it so much. And so now we're going to move into other prerequisite topics away from this particular subject of special relativity. And I'll see you next.